In section 3.2, we're going to be learning the product and the quotient rules, and we'll start with the product rule. I want to just start by giving you two problems that are both asking us to take the derivative of a product. Say I wanted to take the derivative of x squared times x plus x cubed, and let's say I wanted to take the derivative of x times e to the x. Now, inside these brackets, for both problems, I have a product. I have a multiplication problem. But there's a big difference. I can simplify this product. I can do that multiplication. So I haven't yet taken the derivative, but inside these brackets, I can simplify this to x cubed plus x to the fifth. Once I've done that, now I just have a sum of two power functions, and I can take the derivative very easily. So now I'm going to drop the derivative operator because I'm going to actually pass to the derivative. That's going to be 3x squared plus 5x to the fourth. Now with this problem, this is a multiplication problem, but I don't have any way of simplifying it. And that's because here, the two factors are different types of functions. The first factor is a power function. The second factor is an exponential function. Here, both factors were the same type. They were both polynomials. This was a monomial, a polynomial with just one term, and this was a polynomial with two terms. But they were both just sums of power functions. Since they were the same type, we were able to simplify the multiplication. Here, we don't have that option, and so we need to have a rule for taking the derivative of products if we want to be able to evaluate something like this. Now, what I'm going to do in this video is just talk about what the rule isn't. Because based on the sum and difference rules, a lot of people think, hey, the derivative of the product should just be the product of the derivatives. And it is not. Okay? Notice here, if I were just to take the derivative of the two factors, the derivative of x squared would be 2x. The derivative of x plus x cubed would be 1 plus 3x squared. Now if I multiply those together, 2x times 1 plus 3x squared, I would get 2x plus 6x cubed. That is not what I got when I took the derivative of this product. This is the correct answer. This is wrong. Okay? And I want to just take a look at that. I need to first of all find my eraser. I found my eraser. Okay. I want to take a look at why the product rule isn't as simple as the sum and the quotient rules. I'm sorry, the sum and the difference rules. All right, so we're basically saying that the derivative of f of x times g of x is not the same as the derivative of f of x times the derivative of g of x. And at first that feels a little bit weird because we know that the sum and difference rules for derivatives came directly from the sum and difference rules for limits, and we do have a product rule for limits. But let's just take a look at the algebra. If I were to write this as a limit, this would be the limit as h goes to 0. Let's just give ourselves a picture here. If this was my function, f of x times g of x, this would be the point x, and the y value would be f of x, g of x. Our nearby point would be x plus h, and then we'd have f of x plus h times g of x plus h in the y value. And there's our secant line. Okay. And so we would get, let's see, rise over run. F of x plus h times g of x plus h minus f of x times g of x all over h. That's the limit that we should be evaluating. Okay. Now, I'm saying that's not equal to the product of these two derivatives here, which I could write each of those as a limit. So the derivative of f would be the limit as h goes to 0 of f of x plus h minus f of x all over h. And the derivative of g would be the limit as h goes to 0 of g of x plus h minus g of x all over h. Okay. Now, I do have a product rule for limits. Here, I'm taking two limits and then multiplying the result. I could use the product rule of limits to write this as just one limit as h goes to 0 of the product of these two fractions, f of x plus h minus f of x over h times g of x plus h minus g of x over h. So that's legal. This is the same as this. Neither of them is the same as the limit that I would evaluate to take the derivative of the product. But here we can sort of see what goes wrong. If I were adding these two fractions, the denominator wouldn't change. If I add two fractions with a denominator of h, the denominator is still h, which is always what I want to get when I'm setting up a limit of a difference quotient to evaluate a derivative. But when I'm multiplying, the denominator actually changes. H times h becomes h squared. Okay. When I was adding and subtracting the limits that represented f prime and g prime, turns out if I added and subtracted those fractions, I got the difference quotient for f plus g or f minus g. But if I multiply these out, I get a different denominator. I'm going to get a different thing on top as well, because I would have to FOIL this out. So my first terms would give me f of x plus h times g of x plus h. It's starting out looking like I have the right thing on top. But now I get minus f of x plus h times g of x, and then minus f of x times g of x plus h. I don't have either of those terms over here on top. And my last term would be plus, because I've got two negatives that I'm multiplying, plus f of x times g of x. So this is the limit that represents f prime times g prime, the product of the derivatives. It is not the same as this limit, which is what represents the derivative of f times g, what we get if we take the derivative of the product. We do the multiplication, and then we take the derivative. So it's not that we can't use the product rule for limits. It's that when we do the algebra, when we do the multiplication, we get the wrong limit if we just multiply out the limits that correspond to the individual derivatives. So we will be using the product rule for limits as we simplify this, but it's not quite as simple as the sum and difference rules were. So we're going to have to try to figure out what this is, and that's what we'll do in the next video.